Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now, if you find my videos important and interesting to your studies, also please don't forget to subscribe. So here is the problem on the construction of influence line for indeterminate structures. Draw the influence lines for the vertical reactions at the supports and the shear and bending moment at point C of the beam shown below. EI is constant. Plot ordinates to the influence lines every 5-meter intervals. So I will solve this problem by the three-moment equation. Uh, this is the beam is indeterminate to the first degree, statically indeterminate to the first degree. So I select moment at B to be the redundant and apply three-moment equations. So this is the position of the loading for portion AB. Then we will also have a moment equation in general when the position of the unit load is on BD. So 0 plus 2 MB, quantity 10 plus 15 plus moment at D0 plus 1 times x1 over 10, quantity 10 square minus x1 square for 6A1A over L1, 6A2B over L2 is 0 because EI is constant. So 6I is 1, treated 1. Then equal 0 because there's no conditions on support movements. Simplifying, MB is equal to negative x1 over 500, quantity 100 minus x1 square. So for the second position of the loading, call that x2. So take note there's only one unit load and this time it is on BD. So there's no load here. So three moment equations on spans ABD again. Moment at A0. So let's call that 15 minus x2, that's B. So 0 plus 2 MB, quantity 10 plus 15 plus moment at D0 plus 6A1A over L1I1 0, 6A2B over L2I2 is 1, quantity 15 minus x2 over 15, quantity 15 square minus quantity 15 minus x2 square. Simplifying this expression, so 50 MB equals x2 minus 15 over 15, quantity 30 x2 minus x2 square. If you simplify this portion, cancel 15 square. Divide everything by 50, so MB in terms of x2 is x2 minus 15 over 750, quantity 30 x sub 2 minus x sub 2 square. Then next is AY. So let's call this MB. This is the positive direction of MB. So take note that for portion AB, the unit load is still here. So this distance is 10 minus x1. Summation moment B equals 0. So AY times 10 equals 1 times quantity 10 minus x1 plus MB. And MB is given by this expression. So this is 1 times 10 minus x1. And this is MB, which is negative x1 over 500, quantity 100 minus x1 square. Simplifying, AY in terms of x1 for movement of the unit load on portion AB is 1 minus 3 over 25 x1 plus x1 cube over 5,000. By the way, you are not obliged to present the solution in this manner. This is just my style. You may apply method of consistent deformations just like before. So when the unit load is on this span here, so we only have AY and MB. So AY times 10 equals MB, and MB is in terms of x2 this time, x2 minus 15 over 750, quantity 30 x2 minus x2 square. Simplifying, AY is equal to 1 x2 minus 15 over 7,500, quantity 30 x sub 2 minus x sub 2 square. Then for BY, we consider the entire system summation moment D. So don't mind MB anymore, it is internal. So AY times 25 plus BY times 15 equals 1 times 25 minus x1. So again, we sum up moments about D. Considering the entire system, the unit load is still here. Its distance from A is x1. So its distance from D is 25 meters minus x1. So this is the equation. Then substitute the value of AY in terms of x1, 1 minus 3 over 25 x1 plus x1 cube over 5,000 times 25 plus by times 15 equals 1 times 25 minus x1. Simplifying, combining like terms, solving for by. By is equal to 2 over 15 x sub 1 minus x1 cube over 3,000. Next is same equation, and the unit load is now this one. So its moment arm about this is 15 minus x2, and summation moment D equals 0. So AY times 25 plus BY times 15 equals 1 times quantity 15 minus x sub 2. Substitute again AY in terms of x sub 2, which is this. So x2 minus 15 over 7,500 times 30 x2 minus x sub 2 square times 25 plus by times 15 equals 1 times 25 minus x1. Simplifying, combining like terms, solving for by. So 25 over 75 is 1 over 300. Then we have 30 x2 square minus x2 cube minus 450 x2 plus 15 x sub 2 square. We expand this part. Plus 15 by equals 1 times 15 minus x sub 2. So combining like terms, simplifying, by is 1 plus x2 over 30 minus x2 square over 100 plus x2 cube over 4,500. Then ay plus by plus dy equals 1, summation versus y, to derive dy. So that means dy is 1 minus ay minus by. To simplify, you just solve for ay and by, then compute for dy. But if we want to express dy in terms of x1 also, in general, that's the better way. So substitute ay, which is this, in terms of x1. Substitute by, which is this, in terms of x1. So 1 minus ay, 1 minus quantity 1 minus 3 over 25 x1 plus x1 cube over 5,000 minus by, which is 2 over 15 x1 minus x1 cube over 3,000. Combining like terms and simplifying on the next slide. So dy is negative x sub 1 over 75 plus x1 cube over 7,500 after simplifying the expression in the preceding slide. Then for second position, dy equals 1 minus ay, which is in terms of x2 minus 15 over 7,500 quantity 30 x2 minus x2 square minus by, which is in terms of x2 quantity 1 plus x2 over 30 minus x2 square over 100 plus x2 cube over 45. Simplifying, combining like terms, dy equals negative 1 over 7,500 quantity 30x2 square, this one, we cancel negative 1 and negative 1. Then we expand this portion, expand also this portion, or simplify this portion. Then combining like terms, simplifying, dy in terms of x2 is negative x2 cube over 11250 plus x2 square over 250 plus 2x2 over 75. So we now draw free body diagram for portion CD to derive V sub C and M sub C. So when for x1 from 0 to 10, the unit load is not seen here. And even for x2 from 0 to 5, but not including 5, it's also not seen here. When x2 is greater than 5, greater equal to 5, then this is now the free body diagram. And this distance is x sub 2 minus 5. The length of CD is 10, and these are the forces involved in the free body diagram. Considering this portion, V sub C plus dy equals 0, so that means V sub C is negative of dy. Since in terms of x1, this is d sub y, so negative of negative x1 over 75 plus x1 cube over 75. Simplifying, V sub c is x1 over 75 minus x1 cube over 7,500. Then for x2, 0 to 5, this is still the free body diagram. So V sub c is still negative dy, so we just make this negative. So V sub c is x2 cube over 1,250 minus x2 square over 250 minus 2x sub 2 over 75. This is for 0 less than equal to x2 less than 5 meters, excluding 5 meters. When the unit load, including 1 meter, 1 unit load is on portion CD, this is the free body diagram, so V sub c plus dy equals 1. Therefore, V sub c is 1 minus dy. And since this is negative of dy, this one, so V sub c is 1, then plus this expression. So 1 plus this expression, 1 minus dy, or 1 minus this expression. So this the simplification would be this. So 1 plus x2 cube over 11 250 minus x2 square over 250 minus 2x2 over 75. This is for x sub 2 greater than 5. So there are 3 expressions for V sub c. Likewise, for M sub c, considering this free body diagram, V sub c, summation moment about c equals 0, M sub c equals dy times 10. So M sub c is just 10 dy. So we just multiply this by 10 for x1. MC in terms of x1, so negative 75, negative 2 over 15 x1 plus x1 cube over 750. For x2 in this interval, or equal to 5, then we just multiply this by M sub c equals dy times 10. We just multiply this by 10. So M sub c is negative x2 cube over 1125 plus x2 square over 25 plus 4 over 15 x sub 2 for 0 less than equal to x2 less than equal to 5, including 5, because this is moment expressions. For x2 greater than 5, this is the free body diagram. So M sub c plus 1 times quantity x2 minus 5 equals dy times 10. And this is dy in terms of x2. So M sub c is 10 times negative x2 cube over 11 to 50 plus x2 square over 250 plus 2x2 over 75, then plus 5 minus x2 after transposing this to the right. Simplifying, combining like terms, so we have M sub c in terms of x2 for x2 greater than 5 is negative x2 cube over 1125 plus x2 square over 25 minus 11 over 15 x2 plus 5 for x2 greater equal to 5. So let's now summarize everything. MB is negative x1 over 500 times 100 minus x1 square, although this is not required to be plotted, the influence ordinates. And MB in terms of x2 is x2 minus 15 over 750, quantity 30x2 minus x2 square. Then let's plot everything. This is AY in terms of x1, 1 minus 3 over 25 x1 plus x1 cube over 5,000. Then in terms of x2, AY is x2 minus 15 over 7,500, 30x2 minus x2 square. Then let's plot. Let's have also by 2 over 15 x1 minus x1 cube over 3,000. In terms of x2, by is 1 plus x2 over 30 minus x2 square over 100 plus x2 cube over 4,500. So everything is here, so we can easily plot. And these are the ordinates. So I will just explain some ordinates here. For example, MB when x1 is 5. So this is the formula for MB. You just substitute x1 is 5 here, you will get negative 0.75. Another thing, MB is for example 5 just to the right or just to the left, it's the same. So that is x2 is 5, substitute here, you will get MB is negative 1.67. For AY example, when x is 5, you just substitute here, 1 minus 3 over x1 equals 5. 1 minus 3 times 5 over 25 plus 5 cube over 5,000, you will get 0.425. And when when x2 is 10, AY in this expression is negative 0.1333. BY when x is 5, you just substitute here, x1 is 5, you will get 0.625 for BY. And when x2 is 10, substitute here, you will get 0.5556. dy when x is 5, dy here, you just substitute, you will get negative 0.05, or it is equal to 1 minus 0.425 minus 0.625. You will get negative 0.05 also. Then when x2 is 5 left or 5 right, you just substitute the value of x2 here, you'll get these values. Then similarly for dy, you'll get these values. Then v sub c, I'll explain v sub c and m sub c. V sub c, when x1 is 5, you just substitute here, you will get 0.05. Then when x2 is 5 from the left, so this is the formula, substitute 5 here for x2, you will get negative 0.2222. Then when x2 is 5 just to the right, substitute it here, x2 is 5, you will get positive 0.7778. Then when x2 is 10, so this is the applicable formula, you will get 0.4222. For moment at C, when x1 is 5, substitute here, mc here, substitute 5, you will get negative 0.5. When x2 is 5, left or right, it's the same, substitute here, you'll get 2.22222. And lastly, when x2 is 10, you will get these values. And when x2 is 15, of course, everything will be 0 except dy. The unit load is over support D, so naturally dy would be 1. And for x1 equals 10, also x2 equals 0, they are the same. The unit load is over support B, so that's why by is 1, and the rest of the response functions would be 0. So finally, let's have the plotted ordinates. Let's have the computed ordinates to the influence line ready for the construction of influence lines. Let's begin with AY. MB is not important, but we need MB to generalize the expressions for AY, BY, DY, V sub C, and M sub C. So first for AY, it begins with 1, then 0.425, 0, negative 0.1667, negative 0.1333, then 0. So that's the influence line for AY. Next for BY, it begins with 0, then 0.625, 1, then 0.9444, 0.5556, then 0. So that's the influence line for BY. Next for DY, it begins with 0, negative 0.05, 0, 0.222, 0.5778, then 1. So that's the influence line for dy. Then next is v sub c. It begins with 0, then positive 0.05, 0, then negative 0.222, then it abruptly rises to 0.778 just to the right of C, then 0.422, then 0. So that's the influence line for shear at C. Then finally for MC, it begins with 0, then negative 0.5, 0, 2.222 just to the left and just to the right of X2 or C, then 0.778, then 0. So that's the influence line for M sub C. So that's it for this problem. I hope that you were able to follow and understand the solutions as well as the explanations. As I said, you may solve this in your own way, but I solved this in general using the 3-moment equations and the general expressions for moment. Although you can simply solve for B, solve for AY at positions here, 5, then at C, then at this position here. You may not present in general or derive in general expressions for these response functions in terms of x1 and x2, but it's better to have it that way because you will have two solutions to be presented and verified when you're asked to compute for maximum value, for example, for by, for m sub c, or whatsoever. So you just look at the influence lines, then there's corresponding equations for that curve and apply the definition on how to maximize that specific function.